The laws of physics don't care about time. Drop a ball, it falls. Run the film backward, and the same laws still work as the ball flies back into your hand. In fact, almost every fundamental rule of the universe works perfectly fine, forward and backward. And yet time itself only moves in one direction. So where does that arrow of time actually come from? If we look at why physics equations mostly work forward and backward, the answer comes from the basic laws of motion and conservation of energy. Isaac Newton's laws, for instance, describe an ideal world where motion is reversible. If you watch two objects collide on a pool table and you run that video in reverse, the collision looks equally valid. The math works out. When physicists solve Einstein's relativity equations to describe gravity, the solutions are often symmetrical with respect to time, meaning you could flip the direction of time, and the event described still adheres to the rules of space-time and energy conservation. Yet we live in a world where time is fiercely one-directional. No matter how much we want to, we cannot unbreak an egg. We cannot unmix sugar from coffee. We see the world constantly moving from the future through the present and into the past, never the other way around. This difference between the symmetrical nature of physics formulas and our undeniable experience is the great cosmic mystery known as the arrow of time. This difference is why time feels directional. The feeling of time moving only forward is so basic to our reality that we almost never question it. It is what separates the possible from the impossible. We experience growth, decay, aging, and memory, all processes that strictly follow the flow from past to future. This means there must be a rule that forces the universe to move in one direction, even if the fundamental forces themselves don't seem to care. This rule must be so powerful that it overrides the natural symmetry of the rest of physics. It acts like a cosmic clock that is constantly winding itself down, making it impossible to put the pieces back the way they were. The answer comes from the most fundamental concept of chaos and order, the second law of thermodynamics. It is the only law in all of physics that demands a direction for time, and it is the reason your breakfast gets cold and your house gets messy. We need to introduce the simple idea of what entropy actually is. Think of entropy as a measure of disorder, randomness, or the lack of available usable energy in a system. The second law of thermodynamics states simply that in any closed system, disorder always increases. Things naturally move toward chaos. If you spill juice on the carpet, you cannot simply wave your hand and have the juice spontaneously jump back into the cup. The spilled juice represents a system where energy, the juice molecules, is spread out and diffused, which is a state of higher entropy. For the juice to go back in the cup, you would need to concentrate that energy and organize those molecules, which is a state of lower entropy. The universe, taken as a whole, is one giant closed system where this principle is absolute, forcing everything forward toward maximum disorder. The fact that disorder always increases is the most powerful explanation for the direction of time. It is the universal law of messiness. Every single process we observe that feels irreversible, aging, melting, cooling, decay, is an example of entropy winning. Imagine dropping a pristine glass vase. It shatters into countless pieces on the floor. This transformation from one highly organized structure, the vase, to many disorganized fragments, the mess on the floor, is a clear move from a low entropy state to a high entropy state. Why does this process happen so easily? Because there is only one way for the vase to be ordered, whole, but billions of ways for it to be disordered, broken. Chaos is overwhelmingly more probable than order. The second law of thermodynamics is so absolute that it dictates everything from the energy released by the stars to the subtle processes happening around black holes. Take the extreme example of a black hole. Stephen Hawking theorized that black holes slowly radiate energy, a process called Hawking radiation. This radiation means that black holes, contrary to older theories, slowly evaporate over immense timescales. This is where the physics of the very big, general relativity, meets the physics of the very small, quantum theory, leading to a famous conflict known as the information paradox. This paradox suggests that when something falls into a black hole, say a complex object like a star or even a book, all the unique information about that object is erased as it is crushed into the singularity. If the black hole later evaporates, leaving behind only featureless thermal radiation, what happened to the information? Physics states that information must be conserved, it cannot be destroyed. The destruction of information would violate fundamental laws of nature. The most exciting modern view among scientists is that black holes do not erase information. The information must somehow be preserved and stored in the radiation that escapes, though the mechanism is still being worked out. This puzzle forces physicists to believe that the physical laws of nature are being protected, even in the most extreme environment. This preservation is vital because if information could be lost, the symmetry of physics would be completely destroyed. The information paradox is essentially a fight to defend the conservation laws and the reversibility of quantum theory against the irreversible, destructive nature of black holes predicted by classical gravity. The fact that the universe pushes toward disorder affects us directly in how we experience existence. It explains why memories only exist in the past. Memories are high-entropy processes. When we form a memory, we are taking complex information from the outside world and organizing it into specific patterns within our brains. This process requires energy and must follow the arrow of time. Our minds record the transition from a past state to a present state. We remember the disorganized ingredients that went into making the organized pattern of the present. We cannot remember the future because the future, by definition, is still chaotic. It has not yet been arranged into a lower entropy state that we can record. If we could remember the future, it would mean the universe's ultimate state was already fixed and organized, contradicting the constant increase of entropy we observe everywhere. The connection between memory and entropy is crucial because it gives time its personal, psychological feel. We are psychological beings marching into increasing disorder, constantly organizing our perceptions into memories of the past. But if the second law of thermodynamics is so absolute, why does the universe even bother creating structures at all? Why do we have highly organized, low-entropy systems like stars, planets, and complicated life forms? Shouldn't everything just be a uniform, disorganized mess of gas and heat? The creation of complexity, like a star condensing out of a gas cloud or a human brain evolving, is only possible because the total entropy of the entire system, the structure plus its surroundings, increases overall. A star is a highly ordered, low-entropy object, but to exist it must constantly generate massive amounts of energy through nuclear fusion, converting mass into radiation. This enormous outflow of heat and light travels out into the vast, cold emptiness of space, dramatically increasing the disorder of the surrounding environment. The increase in entropy in the environment far outweighs the local decrease in entropy required to form the star. The second law is satisfied, disorder wins, and the universe continues its relentless march toward maximum messiness. This constant push toward maximum disorder means the universe is essentially running out of steam. The total usable energy available is slowly converting into unusable heat dispersed everywhere. To imagine whether time could ever reverse, we must consider what would happen if entropy could decrease. If entropy decreased, shattered vases would reassemble themselves, broken machines would fix themselves, and heat would spontaneously flow from cold objects to hot objects. This sequence of events, called the thermodynamic reversal of time, is considered impossible on a large macroscopic scale due to the laws of statistics. It's like running a universal lottery. Every moment, the universe picks the most statistically likely state for all its matter. Since there are vastly more ways to be messy than ways to be organized, it always picks the messy state. For time to reverse, the universe would need to spontaneously move from a high-entropy state, a massive, overwhelming number of possible configurations, back to a single, specific low-entropy state, a highly organized configuration. The probability of this spontaneous reversal occurring, even in a tiny localized area, is practically zero. This statistical inevitability is why we experience an irreversible flow of time. However, modern physics, specifically quantum theory, introduces a small, strange possibility. The search for a unified theory of gravity and quantum mechanics, often called the Holy Grail of theoretical physics, is forced by the fact that the two theories clash completely at the smallest scales, particularly inside a black hole. Some theorists believe that space and time are not fundamental parts of reality, but instead they emerge from a deeper physical structure, possibly linked to quantum entanglement. If space and time are emergent properties, then their directionality might also be an emergent phenomenon, meaning that at the most fundamental, subatomic level, the reversibility described by simple physics formulas might hold true. But for us, interacting with reality on a large scale, macroscopic, the statistical dominance of increasing entropy ensures that time remains strictly a one-way street. The most profound question about the arrow of time isn't why entropy increases, that is explained by probability. The question is why the universe had to start low entropy. If disorder is the natural state, why did the universe begin in a state of almost perfect order, requiring a tiny, highly specific arrangement of matter and energy? If the early universe were born with high entropy, it would have instantly settled into a uniform, diffuse, messy hot gas. There would have been no complexity, no structure, and no stars or galaxies. The simple fact that structures formed stars, galaxies, and black holes proves that the initial state of the universe, the moment of the Big Bang, was one of incredibly low entropy. This initial low entropy state is what provides the long, downhill slope for the arrow of time to slide down, allowing complexity to emerge as the universe moves toward its high entropy future. The sheer improbability of this original state is mind-boggling. One famous theorist, Roger Penrose, actually calculated the probability of the universe starting with such a specific, low-entropy arrangement necessary for the structures we see today. The odds are roughly 1 part in 10 taken to the 10th power taken to the 100th and 23rd power. That number is so large it's impossible to grasp. It is a 1 followed by a number of zeros equal to 10 taken to the 100th and 23rd power. This number is far, far greater than the number of atoms in the observable universe. This means the Big Bang as the beginning of time was the ultimate low-entropy starting gun. This initial condition allowed the formation of the largest structures in the cosmos. Dark matter, for example, which makes up about 90% of the mass in the galaxy, acts as the invisible gravitational scaffolding that holds massive structures together. Our Milky Way contains gas, dust, and stars, but its structure is dictated by a massive, unseen dark matter halo. Without the initial low entropy that allowed this matter to clump and create gravitational potential, this complex organization would never have happened. The concept of time itself is linked to this process of structure formation. Scientists like Kip Thorne, heavily involved in the discovery of gravitational waves, ripples in space-time caused by massive objects colliding, note that gravity is not a force, but a curvature of space-time. When black holes merge, they send out gravitational waves that are literally oscillations of space-time where time speeds up and slows down locally. This proves that time is not some absolute fixed background, but is interwoven with the physical structure of mass and space. The entire story of cosmic evolution is one where time and space have changed together, driven by the conversion of the universe's initial low-entropy arrangement into increasingly higher entropy states. The constant drive toward maximum disorder is what dictates the eventual fate of the entire universe, often referred to as the heat death scenario. As entropy increases, the universe will become a uniform, featureless mess where all energy is spread out evenly and no more useful work can be done. However, the arrow of time is not just driven by simple decay, it is also intimately linked to the growth of structures across the largest scales of space. How gravity shapes stars, galaxies, and time is dependent on this directional flow. Galaxies like our Milky Way are constantly organized by gravity. At the center of our galaxy lies Sagittarius A, a supermassive black hole with the mass of about 4 million suns. Matter falls into its gravitational well, spirals into an accretion disk, and releases massive energy as it approaches the black hole's event horizon. This release of gravitational energy into light and heat is a dramatic example of entropy increasing. The ordered potential energy of the gas is converted into disorganized, unusable thermal radiation that is dispersed into space. This process is so intense that when supermassive black holes in active galaxies feed rapidly, they generate phenomenal energy output, often in the form of powerful relativistic jets that shoot out at near the speed of light. This energy release acts as a sculptor, pushing surrounding gas away from the galaxy, preventing it from growing too quickly, and ultimately regulating its size. This constant battle between gravity pulling matter in and the resulting energy pushing matter out is the love-hate relationship that structures cosmic evolution. It is the universe using localized high-energy, high-entropy events to maintain the slow, ordered formation of massive structures. The directional nature of time is also the key to understanding the universe's appearance. The solution to the age-old paradox of why the night sky is dark, Olbers paradox, rests on the fact that the universe has a finite age, about 13.7 billion years, and is expanding. Because light travels at a fixed speed, light from distant, ancient stars has not had enough time to reach us, meaning we only see a localized, limited view of the cosmos. This means our cosmic view is intrinsically linked to time itself. We look backward in time the farther out we look. The light from an object 10 billion light-years away shows us that object as it was 10 billion years ago. The universe's finite age is the ultimate proof that it is not an eternal, static place, but a system that began in a highly ordered state and has been moving forward in time ever since. If time could reverse, or if the universe were eternal, every point in the night sky would be blindingly bright from the light that had already traveled infinitely long to reach us. The dark sky is the visual evidence that the arrow of time is real. The irreversible direction of time is ultimately what guarantees the fate of all structures, from galaxies down to subatomic particles. If we return to the question of whether time could ever reverse, we see that even the theoretical conflicts in physics seem to lean heavily toward irreversibility in the macroscopic world. Inside the event horizon of a black hole, space and time are so warped that they swap roles. The singularity, the point of infinite density at the center, becomes not a location in space you can try to avoid, but a mandatory moment in time that everything inside must hit the unavoidable end of time for that object. This transformation is irreversible according to general relativity. While quantum mechanics fights to save information, the information paradox, the practical reality for anything falling into a black hole, is a one-way trip dictated by the geometry of time being fixed and directed toward that endpoint. Time itself is directional because the gravitational collapse is an overwhelming, singular, high-entropy event. The greatest current goal in physics is finding a quantum theory of gravity to understand what happens near the singularity, where our current laws break down. Until then, the existence of black holes and the cosmological fact of an expanding universe both act as irrefutable proofs that time only moves forward. If you want to understand space like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. The universe is a one-way engine, constantly converting its initial, highly improbable, low-entropy state into disorganized, dispersed energy. Every moment of ordered existence, the condensation of gas to form a star, the burning of fuel in a supernova, the complex functioning of a brain that allows you to recall the past, is simply a fleeting, local process, fueled by the overall movement toward universal chaos. The arrow of time is real because the universe started impossibly ordered, and the immense statistical likelihood is that disorder always increases. Time is not an arrow imposed on events, it is the physical march of reality from organization to inevitable disorganization. If you're curious about the force that warps time and space and dictates the fate of stars, but is actually the weakest force in the universe, click here to Why Gravity is So Weak video.